Good evening. Today I'm going to finish up the sensitivity analysis for product mix problem, right? And I want you to recall your memory. In this problem, the company manufactures 5 different products, A, B, C, D, and E, right? And each product requires time on each of 3 machines. So this table shows the machine time requirement, and the unit is minutes per pound, okay? And any amounts that has been produced can be sold, we just assume. And we are given with selling price and material cost like this. And we'd like to determine how many of each product should be manufactured to maximize the profits, okay? And we've defined 5 decision variables, one for each products, A, B, C, D, and E. So for example, A stands for the quantity of product A to be produced, and the unit is pound per weeks, okay? And using this decision variable, we've constructed LP model like this. And I've got this LP formulation from the Lindo. And because Lindo assumes every variable used in the model is non-negative, so the non-negativity restrictions are omitted this time. Okay? And the Lindo provides the optimal solution with some other information like this, which includes objective coefficient ranges and the right-hand side ranges and the final optimal table. Okay? And we are going to use this to answer the questions today. And last time I've covered this question, first question, right? Okay, then let's talk about the substitution rates. What is that? Okay, right here. Okay. This is the final optimal table from Lindo. And the coefficients in the final optimal tables may be interpreted as substitution rates. Okay, that's what we've learned early this semester. And the substitution rates can be understood in the following sense. So like it says, suppose the coefficient of non-basic variable xj in row number I is alpha sub ij. Then this xj variable increases the basic variable in row number I, which is xi, decreases at the rate of alpha ij. Okay? Of course, if alpha sub ij is negative, this means an increase in the basic variable. Okay? So 1 unit of xj substitute for alpha ij units of the basic variable in the optimal solution. Okay? So let's try to answer this question. If we were to produce 10 units of product A, even though it is not optimal to do so, what will be the effect on the profit and the amount of C to be produced and the amount of E to be produced, and finally the amount of unused time on machine number 3. So just ago I said the substitution rate alpha ij indicates how much the xi variable, that is the basic variable in row number I, decreases as xj, that is the non-basic variable, increases. Okay? So in this table, currently the value of uh, 10 units of product A, so we should look at product A, right? Substitution rates for non-basic variable A, right? And this is the current value of these basic variables, right? Because that's the right-hand side values, okay? So if the non-basic variable A increases by 10 units using the final optimal table, we may answer the question. So the profit C, E, and slack variable 4. These are the bases currently, right? I've just got from here, okay? Is the right-hand side value, which is 1817.6, 512, and 3072. Minus, right? And the substitution rate for a variable is 1.38, 1.267, 0.267, negative 4.4 times the A value, which is 10, right? So I would say the profit will be decreased by 10 times 1.38, right? And the production of C will be again decreased by 10 times 1.267. And the production of E will be decreased by 10 times 0.267, right? However, the slack time on the machine number 3 will be increased, right? Negative times negative becomes positive. So the slack time on machine number 3 will be increased by 10 times 4.4. Okay? So everyone knows how to use this substitution rate, okay? Okay, then how do you answer this question, number 3? if 4 hours of overtimes are available on the machine number 1, excuse me, at a cost of $10 per hour, should it be used? So first of all, we've used minutes instead of hours in our equation. So 4 hours means 240 minutes, right? And here, $10 per hour should be $10 per 60 minutes, right? This is $0.1667 per minute, okay? So to answer this question, what information you need to use? The dual price remains valid within the allowable right-hand side ranges, right? That's what we've learned. So first of all, you need to check if the right-hand side value is within the ranges, okay? Here, the allowable increase limit is more than 4 hours, right? Which is 240 minutes. This one, right? So with 4 hours of overtime, the current dual prices for row number 2 which is this value is still valid. Okay? What is the dual price? What does it mean? Dual price of a constraint is the rate at which the objective value will be improved as the right-hand side value of the constraint is increased by a small amount. Okay? And the dual price reported by Lindo for row number 2 is $0.225833 per minute. Okay? And this tells us if the company pays this amount, or if company pays exactly this amount, $0.225833 for an additional minute, then there will be no effect on their net profit. Okay? However, if they pay less than this amount for an additional minute, then the net change in the profit would be positive. Does that make sense? And the cost of overtime which is $0.1667 per minute is smaller than this dual price. Is that right? Which means the company must use the new plan because the net profit will be increased. Is that right? Any questions so far? Okay, then what about question number 4? What is the most that the company would be willing to pay for another minute of overtime on machine number 2. Again, this question tests if you do understand the dual price correctly. Okay? So here, 1 minute of increment is still within the allowable increase limit, which is this, right? 4,388. So with 1 minute of overtime, the current dual price for row number 3, which is this, remains valid. Okay? And again, dual price is the amount by which the objective function value will be improved, given a unit of increase in the right-hand side of the corresponding constraint. Okay? And the dual price reported by Lindo is $0.010833 per minute, right? So this means if the company pays exactly this amount for an additional minute, there will be no effect on their net profit. So the answer is this, 0.010833. Okay? Isn't that easy? Okay, then how do you answer this question? If 4 hours of overtimes are available on machine number 1, again, this is 240 minutes, right? The cost of $10 per hour, same, this should be $0.1667 per minute, right? How the production plan changes. So currently, the row number 2 is this, right? Which is about machine number 1 constraint, right? And by introducing the slack variable, this row number 2 becomes equality constraint. (12a plus 7b AC 10d 7e plus slack 2, right, becomes this right-hand side, 7,680. And the current solution for slack 2 is 0, right, from the window. So this value is 0, which means summation of all other terms should be same as the right-hand side value, right? 7,680. Is that correct? These are the current solution, right? And the revised solution going to be negative 240 for the slack variable on this constraint, which means this becomes 7,680 plus 240, which is 7,920. This is because in order to determine the effect on the production plan of increasing machine number 1 usage by 240 minutes, we must decrease the slack variable, which is the unused time on the machine number 1, from 0 to negative 240. Okay? Are you following me? And alternatively, okay, again, by introducing the slack variable, we have inequality constraints like this, right? If 4 hours, which is 240 minutes of overtimes are available, which means the right-hand side values becomes plus 240 minutes, right? And we still have the same left-hand side. And if you move 240 to the left-hand side, then it becomes slack 2 minus 240, right? Equals the original right-hand side values. Is that correct? And actually, this is exactly the same as what I've done here with revised solution, right? And again, the substitution rate for slack 2, which is slack variable for row 2, so found in the table below, right? So using these values and the current right-hand side values, we can compute profit CE slack 4, right? Those are the bases, current bases from here. Current right-hand side values minus substitution rates for slack variable 2, right? Times how much? Negative 240, right? because just ago we've learned slack variable will take the value of negative 240. Okay? So from the profit here, we must subtract the cost of 4 hours, which is 240 minutes, overtime at $10 per hour. So the net profit will be minus 0.226 to 40. I believe this value is 1869.84. And we need to subtract the cost of 4 hours at $10 per week, $10 per minute. $10 per hour, right? So just subtract 40, which left over $1829.84. Okay? So with the use of overtime, the output of product E will be decreased, right? We have 3 negatives, so E will be decreased. And what about C? C will be increased, right? We have only 2 negative. Does that make sense? Okay, then today we are going to consider another example for sensitivity analysis, which is called Jayer's jewelers problem. So in this example, we assume that the Jayer's jewelers uses rubies and sapphires to produce 2 types of rings. Okay? So the type 1 ring requires 2 rubies and 3 sapphires, and or this one, 2 rubies and 3 sapphires, and 1 hour of jeweler's labor. Likewise, type 2 ring does require 3 rubies and 2 sapphires and 2 hours of jeweler's labor. Okay? And each type 1 ring sells for $400, and each type 2 ring sells for $500. And we assume that all rings produced by Jayers can be sold. And at present, Jayers has 100 rubies and 120 sapphires and 70 hours of jeweler's labor available. Okay? And like it says, the extra rubies can be purchased at a cost of $100 each. The market demand requires the company must produce at least 20 type 1 rings and at least 25 type 2 rings. And we'd like to determine how many of each type of rings should be produced in order to maximize profit. Okay? That's our problem. Okay. Actually, this is the complete LP formulation for this problem. And let's see how we've got this formulation. Because the primary decision is how many of each type of rings should be produced, right? So we define decision variable. X1 is the type 1 rings produced, and X2 is type 2 rings produced. Okay? What else? Because extra rubies can be purchased, right? So we may define another decision variable. Let's say R stands for the number of rubies purchased. So we have 3 decision variables. And our objective function is to maximize J's profit. So maximize the selling price for both types of rings, right? Which is 400 times X1, 500 times X2. Is that all? What about the cost for extra rubies purchased? You need to subtract $100 times number of rubies purchased, right? So this is our objective function. What about the constraint? We do need 3 constraints, one for each ruby, sapphire, and labor hour. Because only 100 rubies are available, and 2 rubies are required for type 1 ring, and 3 rubies are required for type 2 rings. And extra rubies can be purchased. That's why we have first constraint, which is 2 times X1, 3 times X2 is less than equals 100 plus number of rubies purchased. Of course, for Lindo input, every decision variable should be in the left-hand side. Okay? So we may rewrite this constraint as 2x1 plus 3x2 minus R is less than equals 100. Okay? And only 120 sapphires are available, and 3 sapphires are required for type 1 ring, and 2 sapphires are required for type 2 rings. So we have next constraint. And 70 labor hours are available. Only 1 hour is required for producing type 1 ring, and 2 hours are required for type 2 rings. So we have third constraint. And JS needs to produce at least 120. Sorry, is that? No. Only 20 type 1 ring, right? And at least 25 type 2 rings. So X1 must be greater than or equal to 20. X2 is greater than or equal to 25. Of course, non-negativity restrictions are required for each decision variables, right? So these are the complete LP formulation in our case. Okay, right here. Okay. And the Lindo, if you solve the problem using Lindo, then you may obtain the optimal solution like this. The optimal objective function value is 19,000. And according to the optimal solution, the J's must produce 20 rubies and 25 sapphires, and they need to purchase extra rubies. How much? 15. Right? And additionally, Lindo provides more information which can be used for sensitivity analysis. Right? Also, you may obtain the optimal final table like this. Okay? Okay. Then let's answer the first question. Suppose instead of 100, each ruby costs $150. Then would J's still purchase rubies? So currently, J's purchase 15 rubies, right? Because R value is 15, according to the optimal solution. And the new coefficient of the variable R in the objective function would be negative 150 instead of negative 100. Is that right? Which is a decrease of 50. That is less than the allowable decrease in the objective coefficient ranges, which is 100 for R variable, right? And what was the objective coefficient ranges? In the Lindo output, the allowable ranges for objective coefficient represents the amount by which the objective function, the amount by which the objective coefficient can be varied without causing a change in the current basis, the current basic solutions, right? So what can you say about this? The basis will not be changed, right? Which means within these ranges, the value of the variable R remains unchanged. So J's will still purchase 15 rubies to maximize their profit. Okay? Okay, what about next question? Question number 2. To answer this question, again, you need to understand dual price. Okay? Again, dual price is the amount by which the objective would be improved, given a unit of increase on the right-hand side of the constraint. Okay? And the dual price reported by Lindo for row number 4 is 200, right? So this means if J pays exactly this amount, $200 for an additional hour, there would be no effect on their net profit. And the additional profit would be exactly balanced with the additional labor cost. However, if they pay less than this amount, $200, for an additional hour, the net change in the profit would be positive values, right? What about the next question? Your answer in problem number 2 is valid, which means the dual price for row number 4 is $200. That value is valid for up to how many additional hours? So to answer this question, what information you need to look at? Allowable right-hand side ranges, right? Again, just to let you know, the right-hand side ranges for each row are the amount by which the right-hand side values can be varied without changing the current binding constraints, right? Which means within these ranges of values, the current optimal solution remains feasible, okay? In other words, within these ranges of values, the original dual price remains valid, okay? Of course, we assume no other changes occur in the other right-hand side values. And here, for row number 4, the allowable increase in the right-hand side ranges are the 3.3333 hours. Okay? So we may say that up to 3.3333 hours, the answer in problem number 2 is valid. Okay? Which means the dual price for row number 4, which is $200 per hour, is valid. Okay, then what about the next question? If the variable slack 4 were to increase by 1 hour, then according to the substitution rates, the number of rubies purchased would increase or decrease or remains the same. So what information you need to look at? Final table, right? Which is the substitution rates. And we've learned the substitution rates alpha sub ij is how much the xi variable, that is the basic variable in row number I, decreases, right? As the non-basic variable xj increases. Okay? And here, the substitution rate of slack 4 for variable r is positive 2. Is that right? What does it mean? As slack 4 increases, the basic variable, which is r variable, decreases at the rate of 2. Okay? Which means an additional hour of slack 4 would substitute for 2 rubies. Okay? So the answer is decrease, right? Does that make sense? Okay, then what about number 5? If the variable slack 4 were to increase by 1 hour, again, according to the substitution rates, the number of type 2 rings made would increase or decrease or remains the same. Does it remain the same? Okay, here the substitution rate of slack 4 for x2 variable is 0, right? This means changes in slack 4 do not have any effect on the value of variable x2, right? So the answer remains the same. Please interrupt me if you don't follow me, okay? What about next question, number 6? So, or about the same type of questions, okay? If the slack variable 4 were to decrease at this time by 1 hour, then according to the substitution rate, the number of type 1 rings made would increase or decrease or remain the same. Okay, here the substitution rate of slack 4 for x1 variable is positive 1, right? And the positive sign means the change in x1 variable is opposite to that of slack 4. Is that right? So as slack 4 decreases, the variable x1 increases at the rate of this. Okay? So the answer is increase. Does that make sense? Okay, next question is number 7. If we wish to determine the effect on the above solution, if 1 additional hour of jeweler's time were available, we would increase or decrease the variable slack 4 by 1 unit. Here, the labor hour constraint is number 4, right? Again, by introducing the slack variable, we have equality constraint, right? x1 plus 2x2 plus slack 4 equals 70. Is that right? And currently, x1 is 20 and x2 is 25, right? Using these values, this part is already 70, right? So slack 4 should be 0. Now, in our solution, slack 4 is 0, right? So, in order to determine the effect of the manufacturing plan of increasing labor hour by 1 hour, we must decrease the slack variable slack 4, which is the unused labor hour, from 0 to how much? Negative 1 hour, right? Then again, the revised solution becomes 71, this part, right? So the answer is decrease. Is that right? Then what about question number 8? Suppose that instead of $500, each type 2 ring were to have a profit of $400 each. Would Jayers reduce the number of such rings produced? Is that yes or no, or cannot be determined? So this change means a decrease of 100 in the objective coefficient of the variable x2 in the objective function, right? So first, you need to look at the objective coefficient ranges. According to the Lindo report, the allowable decrease of x2 variable is infinity. This means the basis is unchanged for any decrease in the objective coefficient of variable x2. Is that right? This seems intuitive because you will note that the solution indicates Jayers should produce no more than the minimum number of type 2 rings. So a decrease in profit would obviously not make it more attractive to produce these rings. So the answer is no, right? Okay, this is the last question.
So the answer for number 8 is the answer for number 8.
No, yeah. I'm sorry?
Can you explain this again, number 8?
Which part? Number 8 of each part?
How do you say that the answer is no?
Number. This one, right? Because the allowable decrease limit is infinite, right? And in our case, the changes is a decrease of 100, the objective coefficient for x2 variable, right? Because it's within the decrease limit, it doesn't affect anything, right? So the answer is no. Okay, what about question number 9? Suppose that instead of $500, each type 2 ring were to have a profit of $600 each. Would J's increase the number of such rings produced? This is about the same as question number 8, right? So the objective coefficient of the variable x2 has been increased by $100 at this time. So you need to look at the increased limit, right, for x2 variable, which is 200 at this time. What does it mean? Only an increase of 100 is allowable. So the basis will remain unchanged with an increase of 100 because it's still within the allowable increase limit. So the value of x2 remains unchanged. Okay? Any questions? Okay, this is all for today. And next time, I will give you another example for sensitivity analysis. And personally, I think the sensitivity analysis is a very important topic in linear programming. So I will try to give you as many examples as possible. Okay? And let me know if you have any questions regarding these topics. Okay, thank you. I will see you next time.